Welcome to the lesson on continuity or continuous functions. So you might have sort of an idea of what a continuous function means already, or you might not. So here I'll draw you a continuous function. So that's what we would say is continuous. This function looks continuous. Now I'm going to make it not continuous. So what I'm going to do is I'm going to put a hole. So at A, we have a hole. So you know, probably intuitively you can kind of see why we would say this one's not continuous, but the other one is, because it has a break or a hole. So this is what we call a hole discontinuity, or sometimes you call it a point discontinuity. So this one's discontinuous because f at A does not exist. So if the function doesn't exist at a point, then it's not going to be continuous. F at A does not exist. Yeah. Here's another way functions might not be continuous. So you might have that it exists at A, or at all the points, but you get something like this. So let's say this is A, so the function exists there, but then at A it jumps down to somewhere else. So this would be like a piecewise function. You have to define it piecewise. So again, you can see why that's not discontinuous, right? You're traveling along, and then boom, you jump down here. So it's not continuous. So we call that a jump discontinuity. So in this case, why is this one not continuous? Well, notice the limit from one side is not equal to the limit from the other side. So limit as x goes at A from the left of f at x does not equal the limit as x goes at A from the right of f at x. And then there's a third sort of case, and that would be at A doesn't exist again, but it's a asymptote. So A cannot exist sort of as a point or as an asymptote. And we call this one an infinite discontinuity. UIT. So both the right and the limit don't exist, but really it's because there's an asymptote at x equals A. So those are three examples of, and you can see why that's not continuous, right? Because it's going up and then all of a sudden it's way down here. So those are three examples of discontinuous functions. So let's write a kind of a definition of what continuity means. So a function f at x is continuous at x equals A if, so notice we're saying at a point it's continuous. So notice these ones, they were always not continuous at a specific point, just right here and right here and right here. The rest of them, that looks okay, right? That part looks continuous, but not here. So when we talk about continuity, we're going to talk about it at a point. So there's three conditions we're going to have met. The first one, notice in that first example, the point discontinuity, the problem was that f at A didn't exist. So the first requirement on continuity is f at A must exist. The second condition we're going to have to put on, and notice this will come from the second one, right? The problem with this one was the limit from one side didn't equal the limit from the right side. So we had a jump. So we're going to have to make sure that the left and right limits exist. So that basically means that the overall limit will exist, right? Because if the left and right don't exist, then the overall doesn't exist. And now the third case, well, I didn't actually do an example like this, so maybe there should have been a fourth one, but remember this hole, we said f at A doesn't exist. Well, if I put a dot here, right, so f at A now does exist, I'd still say that's not continuous because you're traveling along, and then boom, I'm up here, and then boom, I'm back down here. So it's not continuous, even though f at a does not exist. So the problem here is that f at a is not equal to the limit. So even if f at a does exist, it must equal the limit. So that's going to be our third criteria for a continuous function. So limit as x goes to a of f at x must equal f at a. So the limit has to equal the function at the point. Okay, so this is what it means for a function to be continuous at a point. Now a lot of times you want to talk about continuous functions. So a function is continuous if it is continuous at each point let me reword this. A function is continuous on an interval if it is continuous at each point on that interval. So then you can, if you want to talk about a continuous over its whole domain, then you make the interval the domain. So we can talk about it being continuous at more than just a specific point by giving it, an interval and saying it has to be continuous in that whole interval. And we'll see what that means in a second. Okay, so first example, is this function f at x, it's a piecewise function, continuous at x equals -1. So in order to determine if it's continuous at a point, just go back to, I erased it. Just go back to your definition, right? There's 3 criteria that had to be made. The first one was that the function had to exist at -1. So does f at -1 exist? Does. And the answer would be yes, right? If x is -1, then f at -1 is 0, right? That's this one right here. So good, it exists. The second one is, does the limit as x goes to -1 of f at x exist? Does this limit exist? So in order to determine if a limit exists, you do the limit from the left of f at x and the limit from the right of f at x. And in this case, from the left, so number smaller than 1, I'm using this piece. And let's just notice I can simplify that. Right, I can factor the top. So it's equal to x minus 1, as long as x doesn't equal 1, but that's the restriction. So I can just do the limit as x goes at -1 of x minus 1, and now I can use direct substitution. There's 2, and then I can do the same thing here. And I'm going to be using the same part of the function. Sorry, it's -1. So it'll be -1 minus 1. So the left and right limits exist, so therefore the limit as x goes at -1 of f at x is equal to -2. Therefore, yes, the limit exists. But the third condition is, are f at -1 and the limit as x goes to -1 of f at x equal? And the answer would be no, right? 0 and -2 are not equal. F at -1 does not equal the limit as x goes at -1. Therefore, f at x is not continuous. at x equals -1. Okay, so not continuous. Just to graph it, oops, too far. To graph it, just to see what's happening. So back up to that original function. At -1, we were equal to 0. And then all the other times we were equal to this, which is really just this, x minus 1. So x minus 1 is the linear line. So there was a hole here. Well, I can draw it solid. And then this value was 2. So you can see from the graph that this should not be continuous, right? It's continuous here, yep, continuous, continuous. Nope, jump up to here, jump back down. So not continuous at 1. So from the graph that makes sense.